All right, today we are going to be working a few problems. So grab a paper and a pencil so you can follow along with me. Let's get started. Here is just a reminder of the big ideas from chapter 2. And today we're going to be working several problems involving the big ideas. We will start with something simple at first. So we see that we have an athlete who is sprinting in a straight line. So we've got this athlete moving in a straight line. And it said we're going to take the sprint direction to be positive. So this will be my positive direction. Positive. Okay. The athlete will begin at some point and end over here. And it says the athlete goes 50 meters. So we'll take this to be 0. We want to know the average sprint velocity, the average walking velocity, and then the average velocity for the complete round trip. So we want to know all of this information about the athlete's travel from point A to point B. So let's go ahead and look at the average sprint velocity. Well, let's first just write down that to calculate velocity, we look at displacement divided by time. And to find delta x or delta t, we're going to do a little subtraction. So it's the final position minus the initial position over the final time minus the initial time. So let's plug in the information that we know. Well, we know that this athlete ended the final position for part A when he was sprinting was 50.0 meters. And the initial position was 0. Okay. The final time, well, it says it took this athlete 8 seconds, so 8.00 seconds, minus, well, the initial time was 0. That's seconds. So we end up with 50.0 divided by 8.00. Oh, I forgot my units. And 50 divided by 8 gives us 6.25 meters per second. And this is to the correct number of significant figures. 50.0 has 3 significant figures. 8.00 has 3 significant figures. So when we divide, we need to keep 3 significant figures in our answer. Now, I just did part A, so I would like you to try part B. So pause this video, and when you're ready, hit play. Okay, so part B. We'll choose a different color. In part B, we're going to do the same thing. We're looking at x final minus x initial. So let's just go ahead and write down all this information that we know. And t final minus t initial. Okay. Oh no, I erased my drawing. This is 50.0. This is 0. And this time, the athlete is walking back. So the athlete starts down here at 50 and moves towards 0, back to the starting point. So in this case, my final position is going to be 0. And my initial position is 50. Well, it says that it took the athlete 40 seconds to walk back to the starting line. So the final time, the total time elapsed, would be 40 plus 8, which is 48 seconds. We need a 0.0 because both of these have, this has a 0.0 at 40 and that has 2 zeros, but we go with the least. And the initial time was 8 seconds. So when we do this, we see negative 50.0 meters and 40.0 seconds. So 50 divided by 40, and that's a negative 50, is negative 1.25 meters per second. So that's going to be the average walking velocity. And now we just need to find the average velocity for the entire trip. So let me go ahead and erase this so we can do that. We're going to keep this bit of information. And the final position, well, the athlete started at 0. The athlete started here. And at the very end, the athlete returned there. That means our total displacement is 0. So our total time is 48. And we know that initial time was 0, but our answer is going to be 0 here because we have a 0 on the top. So that average velocity for the round trip is 0 meters per second. Okay, so let's go ahead and try another one. Using the same scenario, if the average velocity during the walk is negative 1.50 meters per second, how much time will it take the athlete to walk back to the starting line? Again, I would like for you to pause this video, try it on your own, and hit play when you're ready. Okay, so to do this one, let's go ahead and list what we know. We know that this is our average velocity. And once again, we know velocity is equal to the displacement over time. Well, we can fill in a couple of pieces of information. Number 1, we know what the velocity is. Negative 1.50 meters per second. And number 2, we know what the displacement is. Because it says, how much time does it take the athlete to walk back to the starting line? So that means the athlete is down at the 50-meter mark. If he walks back, his original position, well, his final position is going to be 0, and his initial is going to be 50, and we do not know the time. That is meters. Well, knowing this, we can just rearrange. And after you rearrange, you should find that delta t is equal to 33.3 seconds. And I did 3 sig figs here because I have 3 sig figs, 1, 2, 3, and 1, 2, 3. So I needed 3 in my answer. So it would take the athlete 33.3 seconds. Next problem. And in this one, we're not going to have to do any math. We're just going to be analyzing a graph. So this is a position versus time graph. And we're looking at this generally. We're going to rank the 6 points, so A, B, C, D, E, and F, and we want to rank them in order of increasing value. So we don't need specific numbers. We're just looking at negative versus positive versus 0. You should immediately notice that there are a few points on this graph that are going to have a value of 0. So these points will have a velocity of 0. We see one here, 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 and here. So A, B, D, and F are all going to have values of 0. Well, even though we don't have any values, we see that C is on a negative slope, and we see that E is on a slope moving up. How do we know that? Well, you read this graph from left to right. So we see that C is on its way down, or the slope is decreasing, and E is on this upward slope. Well, that means that our smallest value is going to be the negative one. So C, oh, you can't even tell that that's a C. Try again. C is first. And then we have several values that are 0. So in that case, we have A, which equals B, which equals D, which equals F. And finally, we have the positive value, which is E. So your final ranking is C, and then A, B, D, and F are all equal to each other, so they go in the middle. They have a value of 0, so we have negative, 0, positive. And you will be asked to evaluate a graph in your quiz, so please make sure you know how to do that. Okay. Right back to the math. This time we are looking at an airplane, and we are told that this airplane has an acceleration of 2.19 meters per second squared. We see that the airplane starts at rest. And remember, if something is starting at rest, that means we know its original position, which is going to be 0, and we know its original velocity. It's going to be 0. So that automatically gives us two pieces of information that we can work with. And it says that the airplane will reach a speed of 174 miles per hour. So our final velocity is 174 miles per hour. Okay, well, we have acceleration. We have some information about velocity, and we have one piece of information about position. We'll see if that's important. Let's write the equation for acceleration. Acceleration, I apologize about how terrible this looks. Acceleration is our change in velocity over a change in time. So we have the acceleration. Oh, and we have V final and V initial. So we can go ahead and calculate delta T. This should be pretty straightforward. 2.19 meters per second squared equals delta V, which is 174 miles per hour. And that's minus 0 over delta T. I am not even sure that y'all can read that, and I'm so sorry again. So for this, I immediately see an issue. This problem does not have dimensional consistency right now. We have meters per second squared right here, and we have miles per hour right here. That is not okay. We're going to need to convert these to the same unit. So pause this video and take a moment to convert miles per hour to meters per second. The only piece of information you might need is this. 1 mile is equal to 1,609 meters. Okay, so go ahead and try that. And I will do this for you. So we have 174 miles per 1 hour. I'm going to convert hours to seconds first. And I know that in 1 hour, there are 3,600 seconds. So that gets rid of hours. and I have seconds. And you could have done hours to minutes, minutes to seconds. That's fine too. Then I need to convert miles. So 1 mile is equal to 1609 meters. Okay. Well, miles cancels, and we are left with meters over seconds, which is what we want. And when you do this math here, you should find that this is equal to 77.8 meters per second. Okay, now that we have that information, let's just plug this back in to the formula. So 2.19 meters per second squared equals 77.8 meters per second over delta t. We do this math and we see that delta t is equal to 35.5 seconds. And that is your final answer. Okay. And let's move right along. Okay, so now we're going to look at a cyclist who's riding in a straight line, and that cyclist has an initial velocity of 3.5 meters per second and accelerates at negative 1.0 meters per second squared for 2 seconds. The cyclist then is going to coast with 0 acceleration for 3 seconds, and finally accelerate at 1.5 meters per second squared for about 2 seconds, for an additional 2 seconds. This is a lot of information. We have a lot of changes happening with our acceleration, so we should draw a graph to help us understand what's happening. I am going to do that now. And maybe I should do it on the next page. Okay, I'm going to do it here. Actually, we're going to go back. So if we're working with acceleration and we want to graph acceleration, we need to create a velocity versus time graph. So we're going to have something that looks like this. V and T. Well, we see here that this cyclist is riding for a total of 7 seconds. So I'm going to put 7 little marks. 1, 2, 3, 4, 5, 6, 7 to mark 7 seconds. And I'm not really sure about the velocity, but I see 3.5. So I'm going to put 1, 2, 3, 4, 5, 6. I'm going to put 6 markings on this. So we have a 6 up there. Oh, this looks terrible. Okay. That looks awful. We're just going to erase that. There's 6. Well, let's look at our first piece of information. We see that the initial velocity is 3.5 meters per second. So my initial velocity is 1, 2, 3, 3.5. So I'm going to put a little dot right here to indicate initial velocity. It is accelerating at negative 1.0 meters per second squared. So that means we're going to have a negative slope here. And if you'll recall, slope is the acceleration, and slope is also rise over run. Do you remember that? Okay, so slope is this, and slope is also acceleration. So acceleration is equal to our slope, and that slope is equal to rise over run. That means we need, for 2 seconds, we are going to decrease that acceleration. Well, we're going to be accelerating in the negative direction for, let's see, 1 goes here, 2 would go here. So let's go ahead and just connect that. That's what our first part would look like. Then it says the cyclist is going to coast with no acceleration. Well, if there's 0 acceleration, that means the slope is 0. So for 3 seconds, we just get to draw a straight line. 1, 2, 3. Okay, now what is happening for those last 2 seconds? We see that the cyclist is again accelerating, but this time in the positive direction. So we're going to have a positive slope at 1.5 meters per second squared. So let's go ahead and move this up 1.5. Let's see, right now we are at 1.5. Well, 1.5 plus another 1.5 is 3, and that'll happen here. And then we're going to move up all the way to about 4.5. So we're going to have something that looks like this. And that's kind of what the cyclist is doing. If this helps you visualize that better, fantastic. I really hope that it does. So our goal is to find the final velocity of the cyclist. Well, to do that, we're not just going to take this point. We're not just going to take the final point. We can't just take that. No. We need to do some math. And we can simply add together the velocities from each section on this graph. So for the first section, let's do our math really quickly. It says that the cyclist is accelerating at -1 meters per second squared for 2 seconds. Well, if you will recall, acceleration is velocity over time. So we can calculate this really quickly. We see -1.0 equals the velocity over 2 seconds. So your velocity for this section is going to be V equals, this is so very difficult to write on, and I am apologizing a lot for that. 2.0 meters per second. And that is velocity over here. In this flat section, well, we don't even need to do any math here. If the acceleration is 0, that velocity is also 0. And on this part moving upward, we have some more information. So we see an acceleration of 1.5, and that is going to occur for 2 seconds. Okay, so that means the velocity over here is 3. Well, let's add those together. So for part A, we see, oh, I'm sorry, I missed a negative sign over here. This should be -2. See, we have a negative here and a positive. So -2.0 meters per second plus 0, we can just ignore that one, plus 3 meters per second gives us a final velocity of 1.0 meters per second. Awesome. So take a moment, and why don't you try to find part B, the average acceleration of the cyclist? And I'm going to erase a little bit of this. So pause and hit play when you're ready. Okay. I'm just going to erase everything. I hope that you have this written down somewhere. I am running out of space. So for this last part, again, A equals dv over dt. We just found that average velocity is 1 meter per second. So it changes by 1 meter per second over the whole time. And this cyclist is moving for 7 seconds, or we are recording his movement for 7 seconds. So 1 divided by 7 to the correct number of significant figures is going to tell us that the acceleration equals 0.14 meters per second squared. So that would be your final answer. Okay. Moving along to the next problem. We are going to look at a ball that has been thrown straight upward. So we have our ball that is, there's a ball, and it's thrown upward. And it has an initial velocity of 7.3 meters per second. The acceleration of the ball is downward. It's going to be the value of gravity. So we want to find the velocity of the ball after 0.45 seconds and 0.90 seconds. Well, In this case, we know the initial velocity, we know the acceleration, and we know the time. What we need to find is the final velocity. So we know these, and we do not know this, the final velocity, V or VF, however you want to write it. Well, do we have some kind of equation that relates VO, well, V naught, acceleration, time, and the final velocity? Yes, we do. One of our equations of motion. In fact, it is V equals V naught plus AT. So let's plug in what we know. We know that that initial velocity is 7.3 meters per second. And we know that our acceleration is negative 9.81 meters per second squared. And the time we are looking at in part A is 0.45 seconds. Once you do this math, you will find that that velocity to the correct number of significant figures is 2.9 meters per second. Okay. Go ahead and try part B. This is very simple. You're just making a quick substitution. Hit play when you're ready. Okay, I'm not going to work out part B. I'm just going to give you the answer. For part B, the velocity is negative 1.5 meters per second. Okay. Now, let's look at one that's a little bit different. Not too different, though. We have a drag racer who starts from rest. Okay, please remember that rest is going to tell us our initial position. So we know x naught. We know our initial velocity. Rest means our initial velocity is 0. We know the acceleration, and we know the time. We want to know how far it has traveled. So we want to know its final position. Okay, this means we want to know x final, which is just x. Well, do we have some equation that relates the initial position, the initial velocity, acceleration, and time? Yes. It is an equation of motion, and it is this one. Our position is equal to our initial position. Wow, this is so difficult. Okay. Our initial position. I cannot draw zeros with this. It is impossible. Plus our initial velocity multiplied by the time plus 1/2 times the acceleration multiplied by the time squared. Well, let's go ahead and plug in what we know. We know the original position, if it's at rest, is 0. So we can just completely get rid of this term. We don't need it. And our initial velocity is 0, which means this is going to go away. So now all we have is that our position is equal to 1/2 times the acceleration multiplied by t squared. When you plug in that information, you find 4 meters per second squared. And our t is, nice and easy, 1 squared. So in this case, our final position is going to be 3.70 meters. Okay, now y'all try part B and hit play when you're ready. Okay, I am just going to give you the answer here. It is worked exactly like the previous portion. And your final position is going to be 33.3 meters away. I I hope you are starting to get the hang of this and figuring out when to use which equations. Okay. We are almost at the end here. Bear with me. This time we're not working with numbers. We are just going to be looking at this symbolically. So we see there's a plane and it's going to accelerate from rest. Again, at rest tells us two pieces of information. We know our initial position and we know that initial velocity. Both are equal to 0. It tells us that this plane has an acceleration of a, so acceleration is equal to a, and the takeoff speed, so our final velocity, is equal to v sub to. So we need to find an equation that's going to relate these together and then rearrange to solve for delta x sub a. Well, if you take a look at those equations that we've talked about, there's only a few which have delta x, but only one that includes acceleration, our final velocity, initial velocity. So, which one is it? Well, it is this one. V squared equals V naught squared, plus 2a times delta x. Okay, so we can get rid of one of these terms immediately. Our initial velocity is 0. That means we have v squared equals 2a delta x. And I forgot to put my little a down here. Well, let's just rearrange this to solve for delta x. Delta x a is going to be equal to v, and I forgot to change that out as well. And that's squared divided by 2a. And that is your final answer here. We're just rearranging equations. And the last problem. We're almost there, guys. Okay, this is just a reminder of your equations of motion in case you have been confused as to where they're coming from. And finally, we're going to look at a free fall problem. So a lemon drops from a tree and it falls to the ground, which is 3.15 meters below. Here is our beautiful tree. And there we go. We have the lemon up here and it's going to fall. And that fall is 3.15 meters. So our final position, x, is 3.15 meters. That initial position, it starts up here. We're just going to say it's 0. Well, how much time would it take for that lemon to reach the ground? So we know the initial velocity. If it drops, that means it started at 0. So that initial velocity is equal to 0. The initial position is going to be 0. And we know that our final position is 3.15. So if it's falling, if it's in free fall, what else do we know? Well, we know the acceleration, and the acceleration is going to be due to gravity. 9.81 meters per second squared. And it'll be positive this time because it is working in the same direction as the lemon is falling. Well, which equation relates v naught with x naught, x, and acceleration? When we need to find t, so t is our question, that is x equals x naught plus v naught t plus 1/2 a t squared. Well, we have some zeros here, so we can just go ahead and mark out a couple of things. We can get rid of x naught. We can get rid of v naught because those are both going to go to 0. Let's plug in the information we know. We know that x is 3.15 meters and that it's equal to 1/2, 9.81 meters per second squared multiplied by t squared. And when you do the math here and you rearrange and you solve for t, you will find that t, I'm going to write this down here, t is equal to 0.801 seconds. So that is how long it would take this lemon to reach the ground. And I will leave the speed for you to calculate. So take a moment to do that. Okay, so let's go ahead and do this last part for B. So we just found T. So now we know the time. We know our initial velocity. We know our acceleration. We know information about the position. So we know X, we know X naught, but we want to find V final, or V. So we want to know what this is. Is there an equation that allows us to relate the velocity to some of these terms in the simplest way possible? Why, yes, there is. It is an equation of motion, and it is V equals V naught plus AT. Well, the initial velocity was 0, so we can cancel this out, and we're left with V equals AT. Let's plug in what we know there. So it's the acceleration is due to gravity. So that's 9.81 meters per second squared. And the time, which we just calculated, is 0.801 seconds. So that final velocity is going to be equal to 7.86 meters per second, and that is to the correct number of sig figs. Okay. If you need additional assistance or you're struggling with this material, please make sure you contact me through Canvas. You will have your study guide for the quiz posted, so work through those problems to make sure you know what you're doing, and I'll see y'all next time.